Okay, we're going to look at mass changes during reactions here. There's a little couple of lines in the AQA specification, and it fits in nicely with reacting mass calculations and a bit of experimental work. So we'll have a look at this. Now, right, here we've got a crucible. This little thing here is called a crucible. You've probably seen one. It's like a white thing. And inside it, we've got some magnesium ribbon. Going to heat it up with the Bunsen burner, and it's going to react, and it's going to turn into magnesium oxide there. It's a white powder. It's quite tricky to do this. You've got to leave the lid slightly off because, of course, you want oxygen to get in there. But if you leave it too open, then a lot of the magnesium oxide will escape as smoke and mess up the experiment. So what you've got to do is you've got to weigh the magnesium before the MG ribbon curled up before, and then you've got to weigh the magnesium oxide powder after you've burnt it. And of course it should be heavier because it's reacted with some oxygen in the air. So you know, we talked about the law of conservation of mass. Magnesium is going to react with oxygen to form magnesium oxide. Okay, so let's balance that. So we need a 2 there and a 2 there. Right, now it appears as though you've gained mass because you haven't really gained mass. It's because you weren't weighing the oxygen to start off with. The oxygen has come out of the air, so the mass of oxygen in the air will be slightly lower at the end of the experiment than it was at the beginning. Okay, so let's just have a look at some results there. So we say the mass of the magnesium at the start equal to 1.65 grams. And they're going to weigh the magnesium afterwards, the magnesium oxide afterwards. And let's say that weighed 2.50 grams. Now, has the experiment worked? Has it given us the expected answers? Let's have a look at that. Right, so let's write the equation again. We've got magnesium and oxygen goes to form 2MgO. So the equation shows us that 2 moles of magnesium will give us 2 moles of magnesium oxide. We don't need to worry about the oxygen. We can simplify that. We can say that 1 mole of magnesium should give us 1 mole of magnesium oxide. Let's work out the moles of magnesium then. So moles of magnesium, use our equation, is equal to mass over mR. It's actually AR this time, really, isn't it? Because it's an atom. Okay, the relative atomic mass of magnesium. So that's going to be equal to 1.65 over magnesium is 24. The AR is 24. And that's equal to 0.06875. I'll leave those numbers in my calculator. So, right, 1 mole gives us 1 mole, so we should get so 0.06875 moles should give us 0.06875 moles. Now we need to work out the mass of the magnesium oxide. I'm just going to move this out of the way. That's the next bit of the video. So I'll get that out of the way. Not letting me do that, so I will. Right, okay. So this is the moles of magnesium oxide. Right, let's work out the mass of the magnesium oxide then. So mass of MgO is equal to the moles times by the MR that is equal to 0.06875 multiplied by the MR of magnesium oxide is 24 for magnesium, 16, so that's 40. And that is equal to 2.75 grams. Okay, now look at our result here. We didn't get quite as much as that. We got 2.50 grams in our experiment. So what's gone on there? Well, probably, as I was saying before, some of the magnesium oxide that was made probably escaped into the air. Okay, so actually we've got a heavier mass, so that wouldn't yeah, we've got less. So we've got less, 2.5. So yeah, a small amount of the magnesium oxide could have escaped into the air, and that's the reason why we're getting slightly less than our calculation showed. Another reason, of course, is because maybe a little bit of the magnesium didn't react. Maybe not all of the magnesium reacted with oxygen. We didn't heat it for long enough, and that would mean it wouldn't get quite as heavy as we would expect. We should expect 2.75, and we got 2.5. Right, let's have a look at another experiment. You can do another mass loss experiment. Right, now this time I've got the diagrams here. Now what we're doing here is we have got some hydrochloric acid, dilute hydrochloric acid, and in the weighing boat there I've got some sodium carbonate solid. Now, sodium carbonate reacts with hydrochloric acid in the following way. You get sodium chloride, carbon dioxide, and water. So let's balance that equation. Well, we've got two sodiums there, so we're going to have to put a 2 in front of that. And that means we need 2 hydrochloric acids there. Okay, now the state symbols are quite important here. So that's a solid. This is aqueous. This is an aqueous solution. Water is a liquid. But the carbon dioxide is a gas, and so that's going to escape. Okay, so what I've shown here is this is while it's reacting. So it's you've taken this weighing boat of sodium carbonate and you put it inside there and you let it react. And it's fizzing because it's making CO2. This is a cotton wool bung here. Okay, so it lets gases out. So the carbon dioxide is going to go out of there. Incidentally, it's a good idea to have not just to leave it open, but have a cotton wool bung there, because you can get little splashes of because it's fizzing, you get little splashes that can come out, and that would mess up the experiment. So the carbon dioxide is allowed out, but the water droplets will stay in. When you finish that, then you weigh the whole thing again. Got the empty weigh boat there. You see that on the balance and the tube, and we should find that it's slightly lighter than it was at the start. So here's the start. Okay, at the start of the experiment, a pen works. Okay, at the start of the experiment, it's going to be slightly lighter, slightly heavier, than at the end, because you've got everything's the same there, except the only thing is you've lost carbon dioxide there. So in this experiment then, we found that the mass of the sodium carbonate at the start was 2.51 grams, and the mass lost, which is due to the CO2 escaping, that was equal to, we measured it as 0.95 grams. Now let's see if this is consistent with what we'd expect. Okay, so the two things we're interested in the sodium carbonate. So 1 mole of sodium carbonate, and we want to know how much carbon dioxide. Well, it makes 1 mole of carbon dioxide. So that's a nice easy ratio. How many moles of sodium carbonate have we actually got? Let's do that. So moles sodium carbonate is equal to the mass over the MR. The mass is equal to 2.51. MR of sodium carbonate, you work it out, is 106. So the number of moles is equal to 0.0237. Okay, so if we've got 0.237 moles of sodium carbonate, we should get 0.0237 moles of carbon dioxide, which is the mass lost. So let's work out the mass of carbon dioxide we'd expect there. Mass is equal to the moles multiplied by the MR. So that's equal to 0.0237. Carbon dioxide, of course, the MR is 44. That is equal to 1.04 grams. Okay, that's equal to 1.04 grams. Now we can see there that that mass is a bit bigger than the actual mass that we recorded, that we lost 0.95 grams, but it's fairly close. I think, you know, that experiment has worked. Probably the reason why this is a little bit less is because carbon dioxide is a tiny bit soluble in water. So what happens is a little bit of the carbon dioxide remains dissolved there in the dilute HCl. It's got a lot of water in it. It's soluble, but when you get too much in there, it's obviously a saturated solution, and the rest of the carbon dioxide comes out as gas. Anyway, just a couple of examples. It's all about reacting mass calculations. That's all it's about.